Hi, I'm Fangyin from Princeton University. I will present our work on modeling articulated objects. Our house has both static and dynamic, or so-called articulated furniture. Reconstructing the geometry, kinematics, and appearance of articulated objects from images is a fundamental computer vision problem with important applications in robotics, AR, and VR. Most prior work is on static objects, from learning to map shape codes to 3D objects, to recovering geometry and appearance for a single scene via differentiable rendering. For articulated objects, many methods model shapes with strong priors and large datasets like human bodies, but we aim for more generic objects. ASDF requires 3D supervision, whereas we only use RGB images and also model appearance. Some nerve extensions learn from hundreds of images to reconstruct a single dynamic scene, but we aim at a category level. In this inverse graphics problem, we need to disentangle different properties from images. Another challenge comes from the unknown articulation with various types and combinations. To tackle the challenges, we model an object with separate shape, appearance, and articulation code. By our definition, the same laptop open at two angles are two articulations. We use IDR as the backbone differentiable renderer, which learns geometry and appearance from masked images for only a single object. We extend it to work for a class of objects with articulation. By first adding the articulation and shape code as input to geometry network. From the predicted geometry and appearance code, the appearance network renders an image from a specific camera view. We impose losses on masked RGB images as well as geometric and latent code regularization. Disentanglement is enforced by for the same object sharing shape and appearance code, and for all objects sharing network weights. Unlike prior work that inputs articulation ground truth, we learn articulation code and will compare in results later. We train our model on Sapien, a public domain synthetic dataset containing over 2,000 articulated objects. We select 9 categories with representative join types and a sufficient number of instances. We first show testing results on synthetic data. We compare ground truth, our appearance and geometry, as well as ASDF geometry. Our method recovers appearance and geometry faithfully using only RGB supervision, as opposed to ASDF, which only estimates geometry and recovers less accurate details and articulations. For classes with 2 rotational joints, our method recovers finer details such as eyeglasses legs, whereas ASDF produces more artifacts like fridge doors glued together. For sliding joints, our method faithfully recovers the topology change between closed and open drawer states, whereas ASDF has a hard time predicting the geometry. For the more challenging class that has both joint types, our method also produces smoother articulation results. Finally, we demonstrate how to animate objects from real-world images by training on synthetic data. We use a cell phone to capture photos of a static laptop, on which we run the model trained on synthetic data to reconstruct the object. Then, by replacing the articulation code with one learned during training, we are able to articulate the static reconstruction realistically for both laptop and drawer. As you can see, since our method only uses images for training and testing, it can be easily set up to test on real data. In conclusion, our method models a class of articulated objects from only images by embedding disentangled geometry, articulation, and appearance. This enables applications such as novel view and articulation synthesis and allows to reconstruct real-world articulated objects by few-shot fine-tuning. Please visit our poster on Thursday afternoon.